Proper subsets introduction. So let's move on to a new idea within set theory. As you recall from our previous discussions, we've been learning about subsets. A subset, simply put, is a set where every single one of its elements is also found within a larger set. Now, on this slide, we're going to zoom in on a specific kind of subset. It's called a proper subset. Think of it as a subset with an extra condition. Understanding proper subsets is really important because it builds on what we already know about subsets and is crucial if you want to have a really solid understanding of set theory as a whole. We'll be looking at how to identify these proper subsets and what makes them different from just regular subsets. In the following slides, we'll be looking at examples to help solidify this concept and also pointing out some common mistakes students make, so pay close attention. Defining proper subsets. So let's move on to formally defining what a proper subset actually is. As we discussed on the previous slide, we're building on our understanding of regular subsets, where all the elements of one set are contained within another. Now, a proper subset is simply a subset that isn't identical to the original set. Think of it as a smaller version of the set, but not a complete copy. Let me put that more precisely. We say that set A is a proper subset of set B, if and only if all the elements of set A are also found within set B, and crucially, set B has at least one element that is not present in set A, so B must have something extra that A doesn't. Now, how do we write this mathematically? We use the notation a subset B, but with a key difference. Notice this symbol, it looks like a subset symbol, but it's open at the top. This open subset symbol, subset, indicates a proper subset. It's really important to distinguish this from the closed subset symbol, which we've likely seen before, that S, subsetec, and it means is a subset of including the possibility that the two sets are equal. So, if A is equal to B, we can still say A is a subset of B using the closed symbol. But if we want to specifically say that A is smaller than B and not equal to it, we must use the open subset symbol, subset. We'll see this distinction play out in the examples coming up, so it's vital to get this straight now. Remember, the open symbol excludes equality, while the closed symbol allows it. Illustrative examples, Example 1. Let's look at our first example to really solidify the idea of a proper subset. Here, we have two sets. Set A, which contains the elements 1 and 2, and set B, which contains the elements 1, 2, and 3. Remember from the previous slides, to determine if a set is a proper subset, we need to check two things. First, we need to verify if all the elements of set A are also present in set B. Looking at our sets, we can see that yes, both 1 and 2, which are the elements of A, are indeed present in set B. Next, and this is the crucial part that distinguishes a proper subset from just a regular subset, we need to check if set B contains any elements that are not in set A, and yes, it does. Set B contains the element 3, and 3 is not found within set A. Because both of these conditions are met, all elements of A are in B, and B has at least one element that it doesn't, we can confidently say that A is a proper subset of B. We denote this mathematically as A is a proper subset of B. Remember that open subset symbol, the one that looks like a slightly curved, is less than sign. That's how we write a proper subset relationship. So, we write a subset of B using that open subset symbol. Keep this example in mind as we move forward, because we'll be comparing other sets to this to make sure we understand the concept fully. We'll see how failing to meet either of those two conditions changes whether a set is a proper subset or not. Illustrative examples, Example 2. Let's move on to our second example, found on this slide. Here we have two sets. We'll call the first set C, and it contains the elements A and B. So C is the set containing A and B. The second set, D, also contains the elements A and B. Now remember what we discussed earlier about checking for subsets. First, we need to verify if all the elements of set C are also present in set D. Looking at our sets, we can clearly see that both A and B, which are in C, are also in D, so that condition is met. Next, and this is the crucial part for proper subsets, we need to check if set D contains any elements that are not in set C. If we examine the sets, we see that D only contains A and B, and those are the exact same elements that are already in C. There are no additional elements in D. Therefore, C is a subset of D, meaning every element in C is also in D, and we denote that relationship as C is a subset of D. I'll say that out loud as C is a subset of D. However, because D does not contain any elements that are not in C, C is not a proper subset of D. This is because C and D are, in fact, equal sets. Remember, a proper subset must be strictly smaller than the original set. This example highlights the difference between a regular subset and a proper subset, and it's important to keep this distinction in mind as we move forward. We'll see more examples, and we'll reinforce this concept on the next slides. Illustrative examples, Example 3. Let's move on to our third example. On this slide, we have two sets defined as follows. Set E contains the elements X, Y, and Z, and set F contains the elements 1, 2, and 3. Now, remember from the previous slides, to determine if one set is a proper subset of another, we first need to check if it's even a subset at all. So, let's check if all the elements of set E are also present in set F. Looking at the sets, we can clearly see that none of the elements X, Y, or Z appear in set F. Therefore, the condition for set E being a subset of set F is not met. Because set E is not a subset of set F, it automatically follows that it cannot be a proper subset of set F either. Remember, a proper subset must be a subset first, and it also must be unequal to the original set. Since it doesn't even qualify as a regular subset, it definitely isn't a proper subset. This example highlights an important point. Before even considering whether a set is a proper subset, you must first establish that it is a subset in the first place. We'll continue to build on this understanding as we move towards the key takeaways and common mistakes, which are coming up next. Key takeaways. Let's recap what we've learned about proper subsets with these key takeaways. First, a proper subset is simply a subset that is smaller than the set it's contained within. Remember, we previously established that a subset contains elements found in another set. A proper subset takes that a step further. It's not just contained, it's strictly smaller. The crucial difference between a regular subset and a proper subset is this: a proper subset can never be equal to the original set. Think back to our earlier examples. If two sets have exactly the same elements, they are equal, and therefore one isn't a proper subset of the other. It's just a subset. Now, let's talk about notation. We use the symbol A is a proper subset of B to specifically indicate that A is a proper subset of B. You'll hear mathematicians say A is a proper subset of B. The symbol itself looks like a subset symbol, but it's open-ended, meaning it doesn't include the possibility of the sets being equal. Finally, here's a concise way to think about it. If set A is a subset of set B, meaning all elements of A are also in B, and set A is not equal to set B, then we can definitively say that A is a proper subset of B. This is a really useful little rule to remember when you're determining if one set is a proper subset of another. In the next slide, we'll look at some common mistakes students make with these concepts, so make sure you've got a good grasp of these takeaways first. Common mistakes. Let's move on to this final slide on proper subsets. It's all about avoiding common pitfalls. A common mistake is confusing the symbols for subset and proper subset. Now, we've been using these symbols throughout, so let's really nail down the difference. Remember that the symbol that looks like a smaller set symbol, with the line being solid, that is, the symbol is a subset of, allows for the possibility that the two sets might actually be equal. So if set A is a subset of set B, it means all the elements of A are in B, and it's perfectly okay if A and B are the exact same set. But when we use the symbol that looks like a smaller set symbol, but with the line being dashed, that is, the symbol is a proper subset of, we are specifically saying that it is a subset of B, but it is not equal to B, it has to be strictly smaller. Another mistake students often make is only checking one condition when determining if a set is a proper subset. Remember, there are two things you need to verify. First, you need to confirm that every single element in the potential proper subset is also found within the larger set. But crucially, you also need to check if the larger set contains at least one element that is not present in the potential proper subset. If you miss that second check, you might incorrectly conclude that a set is a proper subset when it's actually just a regular subset, or even the same set. So, to reiterate, always verify both conditions. All elements of the potential proper subset must be in the original set, and the original set must have at least one element not in the potential proper subset. If you keep those two things in mind, you'll be well on your way to mastering proper subsets.